Well, now it's time to get into some computational formulas. This is the part where you're going to be a little bit easier. I'm going to go easier on you. I won't actually have you do all the computations for all these things. You'll do some, but it won't be as much as you're used to doing. And the place I want to start is in version 8 on page 49 in version 9.477. I want to talk about and see if we could just review for a minute the one-factor ANOVA. Remember the one factor, 2, 3 levels of a product? Do you remember we computed the F, the ANOVA, the F value? Do you remember what that F value was based on? Do you remember it was based on the variance between groups over the variance within? Do you remember that? And you may want to write this in your outline. In a one-factor ANOVA, the F score is based on the variance between groups over the variance within groups. Do you remember what we wanted to have happen there? Yeah, we wanted the variance between groups to be what? Large, because the variance between groups reflects the treatment. So did the treatment work? Are the differences in the means large? The denominator. What did the denominator reflect? The variance within groups. Well, the variance within groups reflected the spread of the scores within the groups. If you're in one particular group, we hope your mean is very different than another group, but we hope that all the people getting the same treatment, that they behave pretty similarly. If they don't, that's considered error. So in a one-factor ANOVA, we wanted a large numerator reflecting treatment effect and a small denominator. The two-factor ANOVA is not that different. And if you understand the one-factor ANOVA, hopefully you're willing to take this leap of faith with me on the two-factor ANOVA. The big word that I learned when I was doing statistics, and it looks like it's on 489 and 477, is the word partition. The idea is, if you look at that stage 1 and stage 2 thing, do you see where it has between treatment variance and within? So for the one-factor ANOVA, the F was the between treatments variance over the within. We hope there was a lot of between, reflecting differences amongst the means, and a little bit of variance within, saying that the scores within the groups are about the same. Now we have a two-factor ANOVA. How many statistical effects are we going to look at? Well, if you remember the previous examples, there are a total of 3 effects we can look at. Is there a significant main effect of variable A, maybe alcohol? Is there a significant main effect of variable B, maybe pills? And then is there a third effect? Is there a significant interaction between alcohol and pills? So in order to actually do the statistics, we're going to actually compute these 3. And if you look at this, you can see that the between treatments variance is actually partitioned into those 3 types. So now what we're basically going to do is, instead of going between over within, we're going to go factor A variance over within, factor B variance over within, and the interaction term over within. So now we're going to get 3 F values as we look at this thing. So I'm hoping that makes some sense for you. If you need to listen to this more than once and read the book, you can certainly do that type of thing. But let's actually go to the analysis here and see what we actually have. So if you look at the partial table that I've provided here, notice I've given you some sums of squares. So let's actually start with that. Notice that in this table, I've given you the sums of squares between groups. Or actually it's called between treatments in those 2 drawings. The sums of squares between treatments is 10,800. So that's a pretty large amount for the sums of squares between treatments.
Any more crumbs?
So with that number being so high, 10,800, that actually reflects the sums of squares between treatment. So that's 10,800. Now let's look at the sums of squares for the alcohol and pills. That would be represented in the drawing below, but notice what we got there. The numbers for the sums of squares alcohol was 4,800. You want that number to be what? Large or small? Hopefully you would answer you want that number to be large. If that number is large, and this is really important, if that number is large, that reflects the fact that the 90 versus 50, the 2 column means, the 90 versus 50, the ones I labeled mm equals 90 and mm equals 50, the more those 2 numbers are different, the larger that value is going to be. So the larger the sums of squares for alcohol is, the more you're going to be able to say, well, it looks like alcohol affects things. So that number is 4,800. You see the sums of squares under that? 4800 for pills. That's going across the matrix. The larger that the no Xanax group is different than the Xanax, the larger that number will be. And notice it's the same number because you're dealing with 90s versus 50s again. So the sums of squares due to alcohol is 4800. The sums of squares due to pills is 4800. The question is, could you actually figure out the sums of squares for the interaction? That is, how non-parallel the lines are. Could you figure that out? Look at it carefully. You've got the sums of squares for the alcohol, main effect. You've got the sums of squares for the pills, main effect. You've also got the sums of squares for the between treatments variance or the between groups variance. Could you figure out how to get the alcohol by pills sums of squares? Hopefully you were able to figure out that you can simply subtract things. Because if you look at the picture in the book, the sums of squares between treatment equals the sums of squares A, main effect, sums of squares B, main effect, and sums of squares interaction. Now it says variance there, but it is sums of squares as well. So if the sums of squares for alcohol is 4800, if the sums of squares is pills is 4800, you add those two up, you get 9600. If you take those two and then subtract them from the between groups treatment sums of squares, then you should get the interaction at a value of 1200. Can you kind of see that? A value of 1200? That's actually what you would get for it. So in this case, we've got the three important sums of squares values. You want those numbers to be high, because the higher those numbers are, the more that you're going to get a main effect of alcohol, a main effect of pills, and an interaction. The final number, I don't know if this is going to be too much for the acoustic tape, but I'll give it, actually, I think I'll stop this one here.